One of the things with yesterday's exam was, and some people noticed this, that was it number 42 with the percent iron? The number was wrong on that, so the percentage is going to come out high. So too high, over 100%, right, is what you were getting, yeah. So it can't be over 100%, it's got to be under. That's what the concentration was, I put in the wrong concentration. It was supposed to be 0.05 rather than 0.5. And so that's why it came out too high. Problem might have seemed familiar.
Yeah, chapter 4.
Yeah, it's from the homework. So it just missed that. Yeah, but anyway, if you got if you calculated the grams of iron, then that's probably enough, for that particular problem. And if you didn't do the percent because it was coming off weird, then that's fine. So do that. There's another thing was there's one other problem, and that was with the air, right? But sometimes this happens. This happens in science. So I was thinking, well, it's always like on the old exam, I didn't correct that. What Tristan found, the kinetic energy was too high. Do you remember that problem? And so there wasn't the correct answer. But sometimes that happens because in science, the way we do science is by peer review. And so through peer review, we do it. Like I said before, there's no solutions manual. When you start working in science, you can't just go to the answer book and check your answer. Is it correct or not correct? And so how do you figure it? Well, you go through it. And you go through it and you go through it. And then if you're confident that you have the correct answer, then, it doesn't matter what the key says. And so what you want to do is you want to boost your confidence level so that you can say, oh, you know what? You made a mistake here. And that happens in science. And then so in that case you want to say, oh, the correct answer isn't here, because you made a mistake, or there's a mistake in the answer keys. And so this happens, and sometimes it's caught right away, because usually what you have is you have a group of peers that review your paper. And so when you turn in a scientific report, you send it off to what are called the referees, and the referees check it. And usually the referees are experts in the field, and you usually get about 3 or 4. And then, they're just sent to people, like, for example, when I was working at UCSB, the professor had a lot of papers that he had to referee, so he would give them to like me and other graduate students at the time to check them. But sometimes that doesn't happen all the time, and so there's something here that was kind of interesting. There's a website called Retraction Watch. Have you heard of this?
No.
These are scientific publications that have to be retracted because of either bad analysis or bad data or other things. And some of these were in pristine, like highly respected journals. Do you know what the most highly respected journals in science are? Like in the U.S., it's U.S. published is Science Magazine, which is really, and they had the Molecule of the Year, And in the United Kingdom, it's Nature Magazine. Those are the two ones that have a very high bar. But surprisingly, there are a number of papers that had to be retracted from Nature and some other, and also some medical journals. And a lot of these are COVID papers relating to COVID, and so you might want to take a look if you're looking at it, because certain things that were once thought were correct, the science, were actually not correct, the science. And so you have to be careful in science. All right, so that was, I was thinking I don't want to, it's a good exercise to be confronted, because that's one of the things that you do once you start working in science is you're thinking, okay, there's always that bit of uncertainty. It's like the unknowns and this kind of stuff. Some things, well, you don't know what it is, because nobody's done it, and so nobody has a key to it. These are all unknowns in a particular respect. All right, so retraction watch, and is a place where you can see, like here, a 2018 letter to the editor of Nature, Human Behavior, etc., and then eventually results in a retracted paper. So this is part of science, and I'll get to you in a second. You understand the material. You understand the material when you don't have to rely on a book or another person, and that would be the level you'd like to learn things at. Okay, Jacob.
Is it okay when I record? It's not
Yeah. Yeah. That's fine. All right, so now what we're going to do is we're going to continue with chapter 7 teaching, so we don't get too far behind. Okay, in chapter 7, we're looking at energy. And we have different units. What were the common units for energy? The two most common ones are
joules and newtons.
Joules and newtons of force. And energy is a little bit more than a force. Like a Newton meter, would be, or something of that sort. Joules would be the most common for chemists, and watts is joule per second. That's a watt. Watt is usually not called energy; it's called power. And so we do watts also.
Bar EK. I think that's what it's
1 watt is a joule per second. With energy. But what are some other units for energy?
Is it bar EK or E bar K?
That's a kinetic energy.
Oh, okay. I'll say it. I don't know if it's bar EK or something else.
Yeah, bar EK. Bar EK is the symbol for energy in this book. Other books will have different symbols, depending on the author. The author often has their own preference. But, this is kinetic energy. And so the kinetic energy could be in joules, or it could be in what other unit is common?
Heat, Q. Q for heat.
Yeah, Q could either be in units of joules, or because heat would be related to kinetic energy.
Yeah.
Or
Would you not put it in Kelvin?
the Kelvin's temperature, but to convert temperature into energy, we need to multiply it by
R.
a constant. So, or if we have a mole, it's R, 3R. And it's, well, I'll just tell you, it's the calorie.
Oh.
Now we have two different kinds of calories. Okay, the joule's defined as lifting a 1 kilogram mass by 1 meter against the force of gravity. And so that's how much work you have to do to lift that. A calorie is defined as how much energy it takes to heat a gram of water by degree C. That was 1 calorie. And then we have a food calorie, or nutritional calorie. The food calorie is equal to 1,000 chemical calories. And so it just makes the numbers a little bit more reasonable because your calorie, can't do that much. So in food, we need, 1,000 food calories or something for a meal. But that would be a lot, 100,000 chemical calories. So that's why we have it. All right. Now, as far as energy goes, that's how much joules or calories of kinetic energy. We have the total energy is equal to what?
Delta Q.
Isn't it potential energy plus kinetic energy?
Yeah. The total energy is equal to the potential energy, which I'm just going to call PE, plus the kinetic energy, which I'll call E sub K. I usually call it KE to match. But he doesn't give us a symbol for potential energy, so we'll just use PE for potential energy. And the symbol that he gives for the total energy is U. Different books will use different symbols for this kind of stuff. And so U is going to be what we call the internal energy. And the internal energy is going to be the sum total of the potential and the kinetic energy, which is just the total energy. So this is internal energy. The situation is it becomes difficult. Kinetic energy, we can measure this pretty easily. All we have to do is measure the temperature. Measure temperature. If we want to know what the kinetic energy is, we measure the temperature and we can convert it from units of Kelvin into units of joules. Using the equations. It depends. If you're dealing with an ideal gas, kinetic energy, the equation's pretty simple because the kinetic energy is just 1/2, mv squared or mu squared. But if you do it in 3 dimensions, then you have to do, and the math might be a little bit more complicated. Or if you do this with rotational energy, into rotational, what else was there? Translational, rotational, and vibrational. Then the equations become a little bit more. It's difficult, but nonetheless, we can get the kinetic energy from the temperature, the average kinetic energy. But what about the potential energy? Can calculate. The potential energy this is difficult to calculate. Let me qualify that. The absolute potential energy is difficult to calculate. And so it's difficult to calculate absolute potential energy. The potential energy has the potential to do something. So for example, if we just take a look at a water sample, like this, the water sample is going to be at 25 degrees C. Well, the kinetic energy is easy. The kinetic energy is a simple calculation. We can relate kinetic energy directly to the temperature. If we wanted to figure out the energies of the motion, that's a little bit more difficult, but just figuring out the average kinetic energy is not difficult. And so from this, the average kinetic energy we can calculate. But what is the potential energy of water? Well, it depends. Is it liquid water? Because the potential energy of liquid water is different than the potential energy of solid water, which is different than the potential energy of gaseous water. And so it depends on the state. So for example, liquid water. Liquid water has potential energy because, you know, it could freeze or it could evaporate. And so there's potential to do stuff like that. And so it can undergo some physical processes. Not only can it undergo physical processes, but it could also undergo chemical processes if we mix it with something. So if we mix something with the water, will it react chemically? That's possible. Or inherently, just water alone, we aren't going to do anything. We just have liquid water here. Is there any energy potential with the liquid water? Yes, that is correct.
I know potential energy is energy that has like resistance to it, and once you remove the resistance, it turns into like kinetic energy?
Yeah.
So
That's
what would be
one.
the resistance for the
Well, one of the resistances for this is how are the water molecules sticking to one another?
pressure?
It's not the pressure.
High in the-
You know, if you go out in space where there's zero pressure, the water still stick. They don't disperse. It's not the pressure that's holding the water molecules down. You know, in a vacuum, the water molecules still stick together.
It's those weak nuclear forces.
It's not weak nuclear
Probably
forces.
bonds.
It's due to hydrogen bonding interactions. Hydrogen bonding interactions are strong, so they hold it together. So there's potential energy in the hydrogen bonds. In order to break the hydrogen bonds, you have to add energy. So we add energy to break the hydrogen bonds, and then when the hydrogen bonds form, this is the first law of thermodynamics, it must, okay, if it requires energy to break, then when they form, it must, release the energy. And so we have energy in the hydrogen bonds. Not only that, we have energy in the hydrogen-oxygen covalent bonds. It costs energy to break those bonds. Not only that, we have energy in the electron in hydrogen and the electrons in oxygen. In order to remove those electrons, it costs energy, correct? And then we have energy in the protons and neutrons, because the protons can be broken up into smaller, actually the nucleus. First off, the nucleus can be broken up into protons and neutrons for oxygen and for deuterium. And so we have energy stored, this is called energy storage, energy stored in the nucleus. And then once we break apart the protons and neutrons, we can break apart the protons themselves into quarks.
Yes.
And the neutrons themselves into quarks.
What are the 4 types of
And then there's actually a lot of quarks, you know, the happy quarks. And,
Up, down, top, bottom, sorry, not this.
yeah.
And then charm and special.
Yeah, there's a lot of quarks. And can the quarks be broken down into smaller particles?
We don't know.
Maybe, yeah. Or maybe not. Maybe that's it. Well, that's all the building blocks of matter. And so the problem is okay, where do you stop? You know, maybe where we stop is just stripping off all the electrons, you know, because chemistry doesn't mess with the nuclei. And so maybe we'll have a relative zero. You know, where is the absolute zero? When have we broken everything apart and then spread it apart by an infinite distance? You know, is that easy to say exactly where the point is when we've taken a water molecule and broken it into as many pieces as possible, and then see, you know, how much energy that costs to break it up and how much energy you're going to get back when you put all the pieces back together? Is that something easy to? No. And so it's difficult to calculate. I mean, if they go to quarks, they can, I guess they can calculate it. But even when they try to calculate it, the error is kind of big. And so there's a large error in the calculations. Large means that the errors make the numbers pretty useless for calculations. And so what this means is this. Oddly enough, we never do this calculation. The kinetic energy is fine, but we never calculate what's called the absolute internal energy. Because the absolute internal energy would require the absolute potential energy. And the absolute potential energy is too difficult to figure. Or kind of large errors in calcs make this number not useful. But we know that there is something, the absolute internal energy. Instead of doing this, what we can do is we could look at delta U. Delta U is the change in absolute internal energy. And so we'll just call it the change in internal energy. And so delta U is going to depend on the change in the potential energy plus the change in kinetic energy. The change in kinetic energy would be a temperature change. What would the change in potential energy be?
A change in state.
Like a change in state. So for example, if we leave the water molecules intact and just go from the liquid state to the gaseous state, then there's no problem. We don't have to worry about tearing apart the atoms and bonds and everything else because the water molecules are still intact. All we're doing is breaking the hydrogen bonds. Well, breaking the hydrogen bonds, that's not that big of a deal. It doesn't cost you a huge amount of energy. And so changes in potential energy can be accurately calculated and measured. This can be measured or calculated accurately. And of course, there's no problem with the change in kinetic energy. So we never use this equation. Delta U is equal to U final minus U initial. Since these guys are difficult to calculate, we never do this. And so what we do is we look at individually the potential energy and the change in kinetic energy when we're doing energy calculations. Now, what we try to do is we try to keep things simple. We try to keep things simple by doing this. So if we have a change in potential energy, we don't want to change the kinetic energy. And vice versa, if we have a change in kinetic energy, we don't want to change the potential energy. In other words, we'd like to keep one of these 0 and then just have all the change in energy due to kinetic, that is a temperature change, or due to potential, some other change. And so this is the way we do it. We divide things into, I divide things into this. I divide things into objects and reactions / physical processes or processes, we'll just call it. Reactions or processes. So what I like to do here is for objects, I like to go like this. Delta U is equal to delta PE plus delta KEK. And what we like to do with objects is to keep delta PE 0. That means the entire change is in terms of kinetic energy. And so when we look at energy changes for an object, let's say I have a chunk of iron or a glass of water. If I have a glass of water, then I don't want it to go from liquid to gas or liquid to solid. I just want it to stay liquid. And then all I want to do is I want to change the temperature. And so what we say is objects heat or cool. And therefore the temperature changes. So I could heat up my water or I could cool it down, but I don't want any kind of what we call phase change. Because that would be a change in. For reactions and processes, I want to keep the PE, okay, but the KE, delta K, or EK, the kinetic energy, we like to keep it 0. So in other words, I don't want the temperature to change. And so here, I'm going to have a reaction or a process. I don't want the temperature to change, but how can you avoid it? Sometimes the temperature changes. And so what we do with this is we make sure that the final temperature is equal to the initial temperature. So let's say it gets hot. If it gets hot, we wait until it cools back down to room temperature, and then we measure everything. Or if it gets cold, we wait until it warms back up. So that let's say we start at 25, we want to end at 25. Or we start at 100, we want to end at 100. And so an example of this would be here. I would do this. If I'm looking at the potential energy change here, I'm going to set the liquid water to 100 degrees C, and I'm going to set the gaseous water to 100 degrees C. So that the final temperature, the gaseous water, and the initial temperature, the liquid water, are the same. So it starts at 100 degrees C, it ends at 100 degrees C. If I start at 25, I have to end at 25. I just got to make sure I do that. And then we can do this. So since we don't measure absolute internal energies, we just have some arbitrary scale on the Y, which we call U. And we just say U increases, but there are no numbers on this scale. It's just what we call energy level. And so we could look at two things. So for example, we could look at here. We're going to look at water. I'm going to take 25.0 grams of water, liquid. And here I'm at H2O liquid at 25 degrees C. And then what I'm going to do is I'm going to increase the energy so that we have H2O liquid at 100 degrees C. And so there's going to be a delta U here. The delta U is equal to U final minus U initial. There's definitely an energy change here, but I don't know what U final and U initial are. You know, U initial is down here, U final is here, but I have no numbers on the y-axis, so I can't measure those or just read them off the chart. Instead, what I'm going to do is I'm just going to look at the change in potential energy plus the change in kinetic energy here. But when I look at the change in potential energy, we start off with H2O liquid, we end up with H2O liquid. Was there any change in potential energy?
No.
No. So delta PE is 0. So the only thing we have is a change in kinetic energy. Well, a change in kinetic energy has to do with temperature. But it's not just temperature because we got to relate it to this. When we try to relate it to the temperature, the change in the kinetic energy here is going to be depending on how much we have, you know. And so the mass of water, which is 25.0 grams, and then we need some kind of conversion factor that relates the mass and the temperature change to energy, and that's going to be this equation. Or we could use a dimensional analysis to figure this out. Mass is in grams. C, do you recall what C stands for?
Joules per gram degrees Kelvin.
Yeah.
In Celsius.
Per degree C. It's called the specific heat. Specific heat has a unit of per gram. Heat capacity could have other units. It could be per mole or it could be per object. So for example, if you want to know, you know, how much heat does it require to warm a brick up by degree C? Do you want to know how many grams of brick you have or just one brick?
One brick.
Just usually one brick. Or how much does it, how much energy does it take to heat up your house by 1 degree C? Do you want to measure how many grams of house you have? No, it's ridiculous. So what we have is we have different units, and we call that the heat capacity. We wouldn't call it the specific heat of the house, because specific heat always has the units per gram. And so therefore we have different heats. And so all these are heat capacities. And so the common units are this: specific heat, joules or calories per gram degree C. That's one. Then we have the molar heat capacity. That's in joules per mole degree C. Or we have the heat capacity of an object. The heat capacity of an object is just going to be in joules per object, one object, per degree C. So the object could be a brick, so this could be joules per brick per degree C. The object could be 2 styrofoam cups with a plastic lid and a temperature probe stuck in there, leaking air and heat to the surroundings. That could be our object, and that object's called the calorimeter. And so the units we have, a lot of people just forget the object and just say joules per degree C, because usually they just talk about one object, and so joules per degree C. And we have different units. And so if we had the specific heat and we knew how many grams, so in this case we do, then we could relate that to delta T here. Delta T. So this is an easy calculation. If I want to find out the total energy change, that is the total internal energy change, delta U, then I just measure the mass, 25.0 grams. C, a lot of people haven't memorized because it's just 1 calorie per gram degree C, and a lot of people have the conversion. How many joules are in a calorie?
4.184.
Yeah, well, 4.184. So this is 4.184 joules per gram degree C times delta T. What's our delta T? T final minus T initial, so that's plus 75 degrees C. So let's go ahead and calculate the total internal energy change for the water. And so that's going to be 25 times 4.184 times 75.
7,845.
Yeah, 7,845 joules. And so this is the total energy change because there was no potential energy change, correct? All right, so this is what we call an object. The object is a beaker of water. The beaker wasn't included though. And so we have something called the system and the surroundings. So in this case, the system was just the water itself. So what must have lost that heat? Well, whatever else is it? Because, energy's conserved. And so if the water gains energy, 7,845 joules, who lost the energy? 7,845 joules worth of energy was lost by something. And since I didn't specify it, then we just say that the surroundings lost it. And so in this case, this is what we define as our system. And that energy must have come from the surrounding. And so this was input into our system from the surroundings. Because the first law of thermodynamics states that energy is neither created nor destroyed. Although we need to modify that. We need to modify that because, did you see that, this thing? What happened? In the news, I just saw it this week or last week.
What's it do?
I'm not
I try to stay blind to everything happening around me. It keeps my mood positive.
There was a, this is not it. What was it, 2023?
I would think.
Oh, here, maybe it was 2022. Scientists managed to take pure energy and create matter.
Oh, I remember hearing something about that.
Yeah. So this was like the first time this was done experimentally. You could predict it, but it's just only energy. In nuclear reactions, we already have matter there, so you can add some matter to it, or you can remove some matter from it, you know, depending on the energetics of the reaction. But this is just taking pure energy and then creating matter, which is pretty amazing. So,
How much energy does it take?
a huge amount, because the amounts of energy are so small that you need very precise, as Alex was mentioning earlier, you need very precise instruments to measure it. You couldn't, you wouldn't be able to measure the amount of mass that they produced here on our balance. Even our fancy $5,000 balances aren't going to measure the amount of mass they created.
Didn't they do this by taking 2 gold nuclei and just smashing them
No,
together
that would be
close to the speed of light?
I don't know what they did, but they're saying pure energy, so it wouldn't involve any gold nuclei, if it were
To create
correct.
energy.
Yeah, they had to create the energy somehow, right? All right, so we have system and surroundings. The surroundings is the rest of the universe, we say. This is equal to the rest of the universe. And so eventually we'll have to modify this, but for chemists, these mass changes and the creation of matter is so minute, it doesn't impact this. We're never going to measure that, and also, these types of things. And so we just treat the first law. People have, thermodynamics has preceded. Did thermodynamics precede, the laws of thermodynamics? I just talked about the first one, but there are multiple laws of thermodynamics. Precede atoms? Did it precede? Who was that person who did the atoms? Dalton's atomic theory?
Yeah.
Did it precede Dalton's atomic theory before most people believed in atoms?
No, I wouldn't think so.
Or did it come after atoms?
I believe it came after.
It actually came before.
Yeah,
When the laws of thermodynamics were developed, there was not widespread acceptance of atoms. Yeah. And so it's kind of weird that thermodynamics came before atoms were widely accepted. And even wide acceptance of atoms, I hear that, for example, the physicists didn't accept atoms. The chemists accepted them first because Dalton's a chemist. Maybe there's some bias there, but it took some time for the physicists to come around, and then eventually they did, and then there was widespread acceptance of it. All right, so here we had the total energy change, and what types of calculations we're going to do is we're going to find out, for example, where can you get this kind of energy? Well, where we can get this kind of energy are from, where?
So if you take 2 nuclei and you smash them together at the speed of light, the protons surrounding them, the small little aura cloud with the electrons, will pass each other at such high speeds that the energy generated is enough to just kind of happen.
Can you heat a cup of coffee with that?
It would take a very long time, yes.
Can you heat up? We're talking in like 10 to the minus 18 joules. When you smash together 2 atoms, 10 to the minus 18 joules, how much coffee will that heat up?
Less than a gram.
Well, it takes 4.18 joules to heat up a gram by degrees C. Is that going to do anything?
I know it's less than 1 gram.
No, you need a mole. If you can take a mole of atoms to collide with a mole of atoms, and then you'll be good. You can heat up lots of stuff with that.
Collide a piece of graphite with a piece of graphite at 50%.
Yeah,
speed
they've been
of light.
doing fusion, nuclear fusion reactions for many, many decades. But they aren't practical. Fusion reactions generate energy, but it's not practical yet. You know, right now they said, oh, you know, there's a lot of stories about nuclear fusion, like the ignition. Oh, we've achieved ignition and we've achieved net energy production.
The lasers.
But you know, they didn't compensate for the energy of the lasers. And so the amount of energy that they input is still less than the amount of energy that they get back. And so it's just how they bookkeep
more
the number.
in the little like chamber of energy. So the laser itself, but to generate those lasers.
Yeah, to generate the laser requires huge amounts of energy.
But the laser itself is
yeah, and so that's not
Yeah.
accurate bookkeeping.
No.
You know, if you got it, if you're proposing a fusion power plant, you got to factor in all the costs. You can't just cherry pick the good numbers there. And so, well, people are looking at fusion to generate this, like using tritium and deuterium to make helium. Have you heard that? And then helium's good, except, you know, during this process, you know what else is released?
Was it radiation?
Neutrons.
Neutron.
Yeah. Problem with neutrons is there's no charge on these. And so what can happen is the neutrons are not going to be repelled. In order to get these, you have to have an atom smasher or linear accelerators, plasma or something. You got to overcome the electrical repulsions. And so you have to either accelerate these, and so you can do that easily. This has been done for many, many years. They can fuse these together to make helium. The problem is can they get a lot of them to fuse together in order to generate enough energy to heat up a cup of coffee? You know, can they heat up a cup of coffee? No, not right now. In fact, the coffee's going to have to heat up the fusion reactor because it's going to cool down. But one of the problems is the neutrons. You know, the neutrons can easily attach to a nuclei, and when you screw up the proton to neutron balance, it creates radioactive nuclides. And so, you know, whatever is containing this is going to become radioactive because of the neutrons. We'll screw it up. And so some people are thinking of avoiding that by using boron instead, but with boron there's even greater repulsions, but that's one of the promising things. I saw a recent video on this. They just need to get higher and higher temperatures for this to work out. But anyway, the way we get it is we'll burn some methane, you know. We can burn some methane and then heat up the water. Well, how much methane are we going to have to burn? Well, we can use stoichiometry to figure it out, you know. What we need what we call the enthalpy of reaction, or the internal energy. So can you tell me what the enthalpy is? I just told you what internal energy is. And this is what makes thermodynamics confusing. Thermodynamics is we have another symbol. You might have seen it before. It's called H, capital H. And how does capital H relate to U and delta U? Well, you need to know that. You need to know that in order to progress in thermodynamics. So thermodynamics is, remember all that stuff with, okay, oxidizer, oxidizing agent, reducer, reducing agent? It gets all mixed up. And the same thing in thermodynamics, it gets all mixed up because all of a sudden we have so many symbols. Not only do we have, you know, when you go into higher thermodynamic levels, you have A, and you have this, and you have that. And there are all these restrictions on this, like it doesn't work in this case, but it works in that case. But people don't keep track of all these things. So that's what makes thermodynamics hard. And so they split thermodynamics up into 2 chapters in this book. The first chapter of thermodynamics is covered in Chem 1A. The second chapter is in Chem 1B, where they throw in some more symbols into this. But we can burn some methane. So, you know, the types of calculations we do is we figure out, you know, if we burn some methane, you know, how much water can we heat up? Or if I want to heat up this water here, how much methane am I going to have to burn to do that? You know, but that's ignoring other things like the beaker. You know, the beaker's got to warm up too. The air warms up, etc. So we try to factor those things in. And so we call this an object. The system's an object here. The next thing we're going to look at is when the system is a reaction or process. So we're going to burn some methane to generate this heat. And so how do I generate the heat? Should I take hot methane and cool it down? If I take hot methane and cool it down and then give that heat to water, then the water should warm up, right? And so is that what we should do? Maybe get some hot, this is not hot methane, but we need hot methane, and then we can warm up the water. We could treat methane as an object. Yeah, we could have hot methane and cool it down. You know, cool it down, it's going to release that energy, warm up the water. And so we could take the object, hot methane, and the object, cold water, and come up with some kind of balance in the middle. It's not going to be directly in the middle because they have different heat capacities. So the heat capacity of water is different than the heat capacity of methane, and therefore the temperatures aren't going to meet in the middle. Right? And so what we're going to look at is when the system is a reaction or process. When the system is a reaction or process, the same thing here, U. What I want is I want this to release energy. And so I want it to be exothermic. My water was endothermic because it's absorbing energy. And so now what I need this to do is release. And I'd like it to release however many joules were required to heat up that water. Okay, now how can I do that? Yeah, I'm going to combust the methane.
Why don't we burn it?
And so what I'm going to do is I'm going to take the methane as a gas. In thermodynamics, we need to know what the state is, because if this were liquid methane, or if this were solid methane, it would have different potential energies. And so methane is going to be a gas, and then I need 2 oxygens to do this. Okay. Now, I know this has higher potential energy than the product mixture. What is the product mixture here?
CO2 and water.
CO2 and water. Now, it makes a difference. If this were gaseous water versus liquid water, it makes a difference. And it depends on what temperature we do this at. You know, what temperature should we do it at?
Hot.
So what I probably should do is, if I want it hot, then what I have to do is I have to preheat the methane. I have to preheat the methane to get it hot, and then I have to preheat the oxygen. Well, just preheat the room. Just turn up the thermostat in the room until it gets hot. Now, how hot should I start it at?
Yeah, but that seems like such a waste of energy.
Yeah.
Why don't we start at room temperature?
Yeah, why don't we start at room temperature? That's a much better idea, I think.
yeah.
Because that way I don't have to preheat anything before reacting it, right? And hey, wait, why don't I start at STP, you know, 0 degrees C? Isn't that even better?
No.
Because we know I memorized the molar volume of the gas at STP. And so I probably should cool it down to 0 degrees C.
But who works at 0 degrees C?
Yeah, nobody. And so this is why we do RT. Right? And this is why I never use that. Okay, now that's a problem, because when you burn methane, doesn't it get super hot? It gets close to 1,000 degrees Celsius. That's the temperature of the flame. 1,000 degrees Celsius. Actually, it depends on the flame too. You have different flames. Not all flames have the same temperature. Some flames burn hotter, some flames burn cooler.
I always try to memorize it as orange is the cooler flame and blue is the hotter flame.
Yeah, yeah. This would be for a blue flame. You know,
So when it comes to metalworking.
methane. Well,
Ooh, it has a higher pressure.
yeah, methane naturally has 900 to 1,500 degrees C. That's usually people. Yeah, maybe 1,000, around 1,000. Butane. This is too cold for butane. 300 degrees C.
The cold flame, low gravity.
in low gravity.
That's weird.
But what does it mean by low gravity?
Working in low
Bunsen
gravity
burner
conditions.
flame is 900 to 16,000, depending on the
This
air power.
no, this is not accurate. This is not accurate because Well, it depends on the burner.
Aren't we still using methane in that case though?
Yeah, we're still using, maybe methane and oxygen. 1600's hot enough to melt platinum. Do you think you can melt platinum with a Bunsen burner?
No, obviously.
No.
But that brings the case
Just
if
the
natural gas is
different
what
source.
happens when it comes straight out the ground.
Yeah, I don't know.
So this is going to go up to, let's say, most people say around 900, 800 degrees C. And so the product, should I write the products at 800 degrees C?
No,
No.
Because there might be a bit too much.
that'd be a change in kinetic energy, and this is
Yeah, and we don't want to change both. Do we want to change both the kinetic energy and the potential energy at the same time?
No.
No.
Because that would be complicating things and also might be a bit too much.
Yeah, it's too much. So what we're going to do is we're going to wait and wait until all the heat dissipates. You know, if you're going to have hot, what's going to happen is it's going to burn, it's going to combust, and you're going to have hot CO2 and gaseous water. And then we're going to wait until all that cools back down and releases the additional heat to whatever. And when that cools back down to room temperature, what's the state of water? Liquid. Going from a gas to a liquid for water releases a lot of energy, so we got to make sure we go to liquid. If you've ever gotten a steam burn, you know, steam can cause devastating burns because there's a lot of potential energy released on that. And so anyway, the difference here is the kinetic energy is the same. And so we could do it this way. This is our U initial. U initial is equal to the potential energy initial plus the kinetic energy initial. And then we have here U final. U final is the potential energy final plus the kinetic energy final. Well, the kinetic energy is the same. And then when we look at delta U, which is the change in potential energy plus the change in kinetic energy, the change in kinetic energy is 0. So we only see a change in potential energy. So at 25 degrees C, methane and oxygen is a much less stable mixture than CO2 and water. This makes sense because if I have CO2 and water, you probably wouldn't worry too much, because you might even drink it because, a lot of people like CO2 and water. They have these machines, you can make it at home.
Carbonated water is delicious.
Yeah, the carbonated water. But if I started filling this room up with methane, would you feel comfortable?
No?
No, you wouldn't feel comfortable because that's filling this up with, combustible gas. And so, there was a recent documentary on, I think it was on Nova or something. It was about the Hindenburg. Have you seen that?
Oh yeah, the German airship that exploded.
Yeah, the German airship that exploded because it was filled with what gas?
Hydrogen.
Really,
Hydrogen gas.
the commercial airship industry.
And
So
yeah, you would think, man, hydrogen gas, why did they choose that?
Because helium's
It
so
has such
expensive.
high chemical potential energy, it's so explosive. And then I found out why they chose that. I didn't know this. It wasn't because they wanted to use hydrogen gas, it was that there was a
Helium shortage.
helium shortage and there was only one place they could get helium.
Us.
Yeah, the US, right. And so there was
Germany ain't gonna go to us.
there's a ban for exporting helium. Right now, helium is hard to come by. It used to be, 10, 15 years ago, you could buy a tank for helium and make helium balloons. But have you? Yeah, I used to have a bunch of those. I got them all the time. But then there was a huge helium shortage. And helium prices skyrocketed. And so we used to use UHP helium, ultra high purity helium, for the mass spectrometer. But a lot of places are looking at alternatives for helium. Oh, but you need it. You need liquid helium to cool magnets. Liquid helium boils at 4 Kelvin. Helium's helium is the most ideal gas around because it stays a gas till 4 Kelvin and then liquefies and then becomes a real gas. But, as the temperature gets colder and colder, it starts to deviate from ideal gas behavior. But anyway, going back to this here, potential energy, high potential energy, low potential energy, kinetic energy is the same, looking at the change in potential energy. Now, the change in potential energy is, we usually measure this kind of stuff because it's kind of hard to calculate. Do you think you can calculate it easily? There are ways we can try to calculate it. One of the most common ways we try to calculate this is by looking at the bonds. You know, how much energy does it take to break 4 moles of carbon-hydrogen bonds? How much energy does it take to break 2 moles of oxygen-oxygen double bonds? And then over here, we're going to have 2 moles of carbon-oxygen double bonds. And over here, we're going to have 4 moles of hydrogen-oxygen bonds. And so what we do is we look at the potential. And normally, one thing is we go from weaker bonds, net, to stronger bonds, net. And so we can calculate it, but those calculations, do you think are very accurate? No. Calculations aren't so accurate because bond energies change. You know, so if you break one carbon-hydrogen bond, the second one's not going to be exactly the same energy because all of a sudden things changed. You know, third one's going to be at a different energy. So we're just taking these averages, which aren't going to be accurate. And so typically we're going to measure this. And so we measure this, and so the equation for system and processes, let me just say, when we have an object, it's just related to temperature. There's a temperature change. And so Q is equal to the amount. I call it the amount, I don't call it mass because it could be 1 brick, it could be 1 gram, or it could be 1 mole. You know? And so I'll just call it the amount times C times delta T. And then we can do that. Over here, when I try to figure out how in the heck, well, I can kind of estimate it, you know, based on the bond energies and that kind of stuff. You know, stronger bonds to weaker bonds or weaker bonds to stronger bonds. In this case, weaker bonds to stronger bonds. Less stable to more stable. And so what this is going to equal is the delta PE here is going to equal delta U. And so what we say here is this. The amount of heat, or the amount of energy, this is energy here, is equal to the amount times delta U of combustion. How much energy? This delta U combustion is typically in units of kilojoules per mole. So for every mole of methane I burn, how much heat do I generate, or how much energy do I generate? It doesn't have to be heat. Heat's often associated just with temperature and kinetic energy, but it's not. Because heat can also be related to potential energy in the sense that we can use that, or the energy is used for heat, or we can use heat to cause the potential energy change. And this is often measured using calorimetry. So specific heats can be measured using calorimetry too. So C's can be measured using calorimetry. Calorimetry is just measuring heat and temperature changes. That's what calorimetry is about. Once we have some of these measured or can calculate, delta U combustion. But when I talk about calculation, we're not calculating at a fundamental level. We're calculating it at a fundamental level. It's the bonds and that kind of stuff. You know, it's the potential energy. But at a different level, we relate it to other things. And so we can calculate it at different levels. Just put a little asterisk there. Well, hopefully we don't have to calculate it. Hopefully we don't have to measure it, because I don't want to do a calorimetry measurement. You know, in the calorimetry, what we do is we ignite our methane and oxygen. But if you do this in a styrofoam cup, what's going to happen to the styrofoam cup?
It's going to burn.
Yeah, it's going to burn. In fact, when we do this, we don't want to use styrofoam at all. Do you know what we want to use?
Tungsten.
We want to use something that looks like a submarine or something. Something that can withstand high pressures and low pressures. You know, in this case, what's going to happen to the pressure? Well, in this case, we're going to use Avogadro's law, and we're at room temperature. So how many, if I had 1 mole of methane, about how many liters of gas is that?
1 mole.
1 mole of methane is about how many liters of
1
gas?
liter.
24.5.
24.5 liters. Or well, let's just call it 25 because I don't want to deal with the points. And so this is 25 liters, plus how many liters of oxygen?
49.
50. So this is about 75 liters. So I take 75 liters, and then my products are going to be, how many liters is this?
25.
25 liters. And how many liters is this?
50.
Oh, that's
This is not 50 liters. This is a trick
That's
question
correct.
because this is not a gas.
Yeah, it's
Avogadro's law just works for gases. This is a
liquid.
liquid. And it being a liquid, 2 moles, 1 mole of water weighs 18 grams. 2 moles of water weighs 36 grams. 36 grams is how many milliliters of water? 36 milliliters. So this is going to be 0.036, 36 milliliters. And so 36 milliliters is kind of small. So what we're doing is we're going from 75 liters to 25 liters. What just happened to the volume? The volume just collapsed. If the volume collapses, do you know what we create?
A vacuum.
A vacuum. So what's that going to do is it's going to collapse the container that it's in. The container is going to do what we call implode. If we went the opposite direction, the container could explode. And so we got to watch out for implosions and explosions. And so we don't do this. Like for example, over here, you know, if we're just heating up water, then we can use what we call coffee cup calorimetry, which we did. Let's talk about it later. Over here, the calorimetry that we have to use for this kind of thing is bomb calorimetry. And so we have 2 types of calorimetry. The 2 types of calorimetry are coffee cup calorimetry. But is a coffee cup a sophisticated piece of scientific instrumentation? No. No, it's not. And so this is just, it's cheap, but they're more better, like, you know, double vacuum walled containers or whatever else that we could use. And so instead of calling it coffee cup, I call this constant pressure calorimetry. The other type of calorimetry we have is something called bomb calorimetry. And so we're either going to do it in a coffee cup or we're going to do it in a bomb. Why do they call it bomb? Because it might explode like a bomb, you know, if the pressure goes too high. Or it might implode like a, some other type of bomb. Nuclear bomb.
Oh no.
But anyway, here, this is called constant volume calorimetry. Now the next thing in thermodynamics is very important to know. Are you working under constant pressure conditions or are you working under constant volume conditions? Because you know what? It changes the amount of energy potentially. So if I burn methane in a bomb, do you know I'm going to get a different amount of energy than if I burn methane in a coffee cup?
Yeah.
And so I got to be aware of this. And so I need to know what conditions I'm doing this under. Now, when you burn methane, do you usually burn it in a bomb? Or do you usually burn it in the, well, you probably don't burn it in either of those, but what conditions would you say? Constant pressure or constant volume?
Pressure.
Constant pressure. So when we deal with thermo, we usually deal with Avogadro's law or Dalton's law?
Avogadro's because it's constant volume.
not
Constant pressure, sorry.
constant pressure, right? And so everything's Avogadro. So when I think about this, I think about mixing 25 liters of this and 50 liters of this. You know, I don't think about mixing 25 liters of this and 25 liters of that, right? And the 25 liters of this is going to be double the pressure because I have twice as much gas. We don't usually do that. But let me take that back. We don't usually do that unless I'm doing it in a bomb. If I'm doing it in a bomb, then I'm doing it under what conditions?
Constant volume.
Under constant volume conditions, which means I have to think of all mixtures in terms of Daltons or in terms
Daltons.
of Avogadro? In terms of Daltons. So if I do it in the bomb, I shift my thinking. And so I have two universes I occupy. I either occupy the constant pressure universe or I occupy the constant volume universe, and I don't mix them up. If you start mixing them up, you're going to screw up all your calculations. And so, you know, people screw up all their calculations in thermodynamics. This is why there's a debate about what the hardest class is. I think. Oh, this is kind of interesting.
I feel like that debate's kind of silly though.
It is.
I would say there is no hard class. It's just every class has a different difficulty because each one delves into a different topic.
Yeah.
It's like the difference between soccer and basketball. Two different muscle groups.
Yeah.
The difference between FPS and world builders.
I guess it doesn't even come up. There's an ongoing debate.
Oh, there's a Chem 4450.
It's like this Harvard student born. There's an interesting debate about what's harder, thermodynamics or organic chemistry. Thermodynamics is pretty hard. I mean, it's called physical chemistry, and they sell bumper stickers at UCLA.
I passed them.
I passed. Did I already mention that?
You mentioned that once before.
Yeah. Okay. I'm repeating myself then.
Do you have a bumper sticker like that?
No, I didn't buy one, but a student of mine bought one for me. So I have one now. But I haven't put it on the car yet. I'm too
Professor,
embarrassed
you're missing
to put it
out on the
car.
club.
Yeah. But anyway, so we got to keep track of these things. So then my thinking goes, okay, if I'm in the constant pressure universe, then I'm thinking this way. If I'm in the constant volume universe, I'm thinking this way. And we have to keep these things separate. And we can keep these things separate with symbols like U. U works in U works, U is called the state function. And so whenever I burn methane, I'm always going to get the same amount of energy. This delta U is always going to be the same. And let me just do this one.
Professor, I have a question.
Uh-huh.
With thermodynamics, what does the H stand for?
Okay.
Or should we even know?
Yeah, you need to know.
Okay.
What does the H stand for? Does somebody have the definition for me?
Heat of the reaction.
The capital H, yes.
All right, let's see what this is. People also ask, what is internal energy heat of combustion? The terms heat of combustion and enthalpy of combustion are used interchangeably due to the first law of thermodynamics and the relationship between the heat at constant pressure, QP, the change in internal energy, and the change in enthalpy. So what's going on here? Delta U is equal to QP minus P delta V. All right, so what's going on here is this. So we're going to keep track of these types of things coming up. And so this is where the energy is going to come from. We're going to do a calculation. Now, this is what we call a bomb. This delta U we use in a bomb. You can figure out what delta U is using bomb calorimetry. There. Because when you do it in a bomb, does it matter what's happening with the rest of the universe? It doesn't matter what's happening with the rest of the universe because you have your gas and you're burning it in the bomb, and the bomb's not allowing it to interact with
The universe.
the rest of the universe. It's isolated to the bomb, although the bomb can get hot. Obviously, the bomb's going to get hot, so we need to know what the heat capacity of the bomb is. Okay, the situation here is this. When you blow up a balloon, does it cost energy?
Yeah.
Yes,
Yeah.
yes.
And how much energy does it cost?
Is I have to write it down. It's 25.7. No. Wait. That's way too far back.
Do you recognize this equation? This is the first law of thermodynamics. All the first law says is that if there's an energy change, energy is neither created nor destroyed. And so if something loses energy, this is going to lose energy. Where does that energy go? We're going to ignore mass production, because the amount, it could go into mass formation, but the amount of mass here is going to be negligible. Where's most of the energy going to go? Most of the energy is going to go into, well, what do you do when you burn methane? You could do two things when you burn methane. One, you could heat a pot of water, right? So I could heat up a pot of water. And the other is I could do work with that. And we have different kinds of work. And so this is heat, and this is work. Heat is just warming things up or cooling things down. Work, we have lots of different types of work. So the work, what types of work do we have? Well, when I burn the methane, have you seen those buses that have that little CNG on them? CNG. Like, for example, when I follow a bus, I usually turn on the recirc on the air because I don't want to breathe the NOx, from the diesels. I try to minimize it. They smell bad, and they're bad for your health, right? And diesels, I hate following diesels. It's like following crop dusters, But the CNG buses, I don't turn on the recirc. If I'm following a CNG bus, then I don't really worry about it too much because the CNG buses, do you know what they burn? Methane, compressed natural gas. Compressed natural gas burns pretty clean, so I don't worry about NOx there. And so we can have mechanical work. And so when you burn the methane, it's like burning gasoline, and you have an engine there, and you have pistons and all that kind of stuff, and it starts rotating something. And so we have work that's mechanical. Are there any other types of work? Well, there's other types. Have you seen those, what they call the methane fuel cell vehicles? Those are a lot rarer, but there are some methane fuel cell vehicles, and they work differently than the methane buses. The methane buses just run some kind of engine, but methane fuel cell converts the methane directly into electricity. Yeah, and so we can create electrical work. Plus, etc. Noise. If you have a methane explosion, you hear that noise. That noise is not heat. That noise is work. Or maybe the methane explosion breaks your leg. And so if it breaks your leg, some debris hits your leg or something, then that is
Work.
work. And so we could have lots of different kinds of work here.
Just got work done.
And so we need to know, it depends on how much work this does. How much work does this reaction do? And that's going to tell us how much heat, because the work, is going to change the amount of heat. So if you're converting all this methane into electricity, you want minimal heat. That is, you want to bring the heat down to zero if possible and use all that energy to convert it into electricity. But the problem is that possible? No, it's not, unfortunately. I mean, you can minimize it. Or, if it's cold, then we don't want to do any work at all. We want all the methane combustion to go into heat. So in the lab, I don't want any light to come off because light is work. Light is photons, and photons are these things of light we'll talk about later. I don't want any light, I don't want any sound, I just want only heat to come off this because all that's wasting energy. And so it depends on how we combust the methane. And how we combust the methane at the two simplest levels would be, are we going to combust it in a bomb, or are we going to combust it, are we going to combust it at constant volume, or are we going to combust it at constant pressure? Because that's going to make a difference in this because of one type of work. So the most important work for us under constant pressure conditions is what we call pressure volume work, PV work. So if we do this reaction in a bomb, the volume can't change. Delta V is 0. And so we can do this in a bomb. Delta V is 0. There's no change in volume because the volume has to be constant. If there's no change in volume, then there's no PV work. If there's no PV work, then all the delta U goes into heat. And so we could heat up our water. But if we do this in a coffee cup, well, literally we aren't going to use a coffee cup, then we just figured out what is delta V for this. Delta V is about minus 50 liters. Well, to blow up a 50-liter balloon, is that going to cost you energy? And what do you think the pressure is going to be? What pressure do you want to use for this?
1 atmosphere.
1 atmosphere. So we'll just say pressure is 1 atmosphere, just normal pressure. So if you blow up a 50-liter balloon, that's going to cost you energy. How much energy does it cost to blow up a 50-liter balloon? Well, actually, we can calculate that. PV work is a very simple equation. The work is equal to minus P delta V. It's going to be negative. Pressure is always positive, and if we blow up a 50-liter balloon, that's positive. So in this case, as an example, this is going to equal minus 1 atmosphere times the delta V of 50 liters. And so this is to blow up a 50-liter balloon. And how much energy are we going to lose? We're going to lose 50 liters atmosphere worth of energy. Well, what are the units here? The units are going to be in atmospheres, liter, what am I doing? Liter atmospheres. Atmospheres, liters. That's not joules. That's not calories. But there is a conversion that we can use. And the conversion is that there are going to be 101.3 joules for every liter atmosphere. So if I wanted to blow up if I wanted to blow a 1 liter balloon, you know how much energy it's going to cost? 101 joules. If I want to blow up a 2 liter balloon, it's going to cost me 200 joules. So if I want to blow up a 50 liter balloon, it's going to cost me
5,050.
Yeah, 5,050 joules.
Or 5,051.5.
Okay, 5,051?
Yeah.
Okay. So in other words, I'm going to have to lose 5,000 joules worth of energy to blow up a 50 liter balloon. Right?
Yes.
If I wanted to blow up a 50 liter balloon, but I don't want to blow up a 50 liter balloon because it's a lot. I mean, how many Big Macs would I have to eat for that? That would be another thermodynamics calculation. Maybe only one.
2 Big Macs.
2 Big Macs? Okay.
Yeah. 1 for good luck.
But this is weird because what's happening here is I'm not blowing up a balloon, right? In fact, the balloon is collapsing. I have a 50 liter balloon that just collapsed to nothing. Does that cost me energy? So to deflate, if I popped a 50 liter balloon, is that going to cost me energy? No, so it's free. So in this case, is it 0?
No.
No, it's not 0 because first law of thermodynamics states that energy is neither. So somebody just lost 5,000 joules. Who lost the 5,000 joules?
The balloon.
Not the balloon.
No.
Not the balloon. Who lost the 5,000 joules?
The surroundings.
The surroundings lost it.
I was gonna say the surroundings, but
If not the system, then it has to be everything else.
Yeah, everything else lost it. You know what? So let me just say, the point of this is this. You get more heat burning methane under constant pressure than in a bomb. That extra heat comes from the surroundings. We'll stop here.